Okay, well, hi everyone. Welcome in Music 250A. I'm Roman Michon, and I'm going to be the main instructor for this class this quarter. And Mike Molshine, are you here, Mike? Or
Yep.
okay,
Hey, how's it going?
perfect. And Mike is going to be our TA. Yeah, before I get started, just want to say a couple of words about myself. I teach at CCRMA 1 quarter per year, and this time it's in winter, and I teach this class. The rest of the time, I'm a faculty researcher in France at INRIA, which is a research institute for computer science, and it's based everywhere in the country. So yeah, that's me. Maybe Mike, you want to say something about yourself before we move on?
Sure. Hey, I'm Mike. I think I know most of you. I'm a third year PhD candidate in the CCRMA program. Um, and I do a variety of things, mostly centered around interaction design, whether that's digital or physical. And I'm a musician as well. And so, yeah, I'm just excited to be involved and happy to help in any way I can.
Cool. Yeah. Thank you, Mike. Yeah. I guess I didn't really say anything about what I do besides teaching Music 250A. So I do research, and I mostly do research on embedded system for real-time audio signal processing. So most of the research that I'm doing these days is related to the Faust programming language, which we are going to use as part of this class, and FPGAs, which are field programmable gate arrays. And so for those of you who've never heard of FPGAs, that's something that we'll talk about later during the quarter. Okay. Cool. So before we have our first lecture, I just kind of want to give you an overview of what we're going to do this quarter in Music 250A. So the main resource for this class is going to be the class website, which is carma.stanford.edu/courses/250A. If you haven't visited it yet, I strongly recommend you to do it today because all the useful information for this quarter are going to be posted on the website, which is going to be updated towards as we move on in the quarter. So as I'm sure you know already, classes are going to be Mondays and Wednesday between 9:25 and 11:15 a.m. We might stop a bit earlier today because we're doing this remote format, and so this is the normal time if classes were going to happen in person. But yeah, we'll see how things go today. But it's possible that we stop at 11 because I know that. Doing like a full 2 hours class on Zoom can be kind of a pain for you and for me too. So we'll see how this goes. We're gonna have labs, and so the what we call labs are mostly office hours. There's gonna be labs every week. So in addition to the classes, you're gonna have like tutorials and labs to do, and then you're gonna have assignments. And Mike and I are going to be here to help you do these assignments. And we need to figure out when those are going to happen during the week. So I think the best way to do this is we'll probably send you a poll at some point today or tomorrow to figure out times to do office hours and labs. Usually, I would say that Mike will probably do 2 sessions of office hours during the week, and as for me, I can have 1, and also I'll be probably most of the time in the Max Lab, and so if you're on campus, you're more than welcome to just come, or just make appointments or whatever. By the way, this is the Max Lab, so this is a resource that we're going to use heavily during the quarter. Well, hopefully. and so the Max Lab is basically the CCRMA prototyping lab, and it's very well equipped with 3D printers, everything you need to do like soldering, basic electronics, and etc. So this is really a room that we're going to use a lot during the quarter, and eventually we'll give you a tour of it, and hopefully that will happen in person probably on week 3. Anyway, so there is a required textbook for this class, which is a textbook by Gat Wong, who's a faculty at CCRMA as well. And the name of the textbook is Artful Design, Technology in Search of the Sublime. So if you haven't already, if you don't already have it, you can just buy it on Amazon, by clicking the link on the website, and it's probably available at the Stanford bookstore as well. Okay, to take this class, there is no proper prerequisite. I would just say that you sort of need to have some kind of experience in programming in general. And in this class, we're going to do a lot of different things. It's a very broad and cross-disciplinary class where we're going to do electronics, we're going to do programming, we're going to do basic signal audio processing, embedded systems, 3D printing. So a lot of different things, basically. And so I would say that having some programming experience is important to be able to take this class, because it's definitely going to save you a lot of time in terms of catching up with some of the concepts that are going to be studied in the class. So speaking of the topics of the class, we're going to talk about sound synthesis, and that's something we're going to do mostly in the first 2 weeks of the quarter. So if you haven't done sound synthesis before, we'll sort of get you started on basic sound synthesis techniques like wave shape synthesis, additive, subtractive, AM, FM, etc. And this is just going to be a very broad overview, and the goal is not necessarily for you to completely understand the way these techniques work, because there are other classes for that, but more like to be able to use them and to sort of have a basic understanding of how these techniques work when you implement them in a programming language for computer music or real-time audio processing. We'll talk about sound processing in general, so like audio effects, basically modulation, flanging, phasing, chorus, etc. And it's kind of the same story as for sound synthesis. We just want you to get a basic understanding of all these techniques. We'll be heavily relying on the Faust programming language. The Faust programming language is DSL. It's a domain-specific language, which is specifically designed for real-time audio signal processing. And so that's the reason why we're going to use it as part of this class. There are other languages that exist that we could have used for that, but you'll understand pretty soon why we're using Faust, because Faust allows us to do things that other languages would not allow us to do, for example. And I'll talk more about this in later in the quarter. I think at this point it's just to give you an overview. We'll talk about microcontrollers programming, and mostly we're going to be programming microcontrollers, which are called the Teensies, and you're going to get them as part of the kit, because if you take this class, you get a kit. I'll talk a little bit more about the kit later. We will do embedded system for real-time audio DSP. So, we will learn how to program them, and we'll try to study some a little bit more advanced topics like bare metal audio systems for ultra low latency and things like that. Which is also going to happen on the Teensies. We'll study fundamentals of electronic sensors and prototyping. Really fundamental things about this. We will look at computer-assisted design and digital fabrication, mostly 3D printing and laser cutting. We have a laser cutter here at CCRMA. There are laser cutters on campus at the PRL, the Product Realization Lab. And you're going to have access to the CCRMA laser cutters and 3D printers, and so this is something you get as part of this class. We'll talk about digital lutherie, so basically musical instrument making and musical interface design. And finally, we'll talk about haptics as well. Okay, in terms of evaluation, as you can see, there will be assignments every week until week 6, okay? And after week 6, we'll switch to final project mode. So, so it means you're gonna have 6 assignments to do as part of this class, 1 per week. Yeah, assignments will count 50% towards the final grade you're gonna have in this class, and final project 50%. So I don't know if you heard about Music 258, but before actually enrolling in this class, but it is a fairly time-consuming class. Just so you know, you sort of decide how much work you want to put into it, but you know, I would say that it's fair to assume that beside classes and labs, you should probably assume you're going to spend at least 6 or 7 hours per week on assignments. You know, and it's possible that for some assignments you can sort of reduce it. You know, because assignments are really just making small projects, basically. You know, so it all depends on how much time you want to spend into it. But you know, whenever you start doing hardware, things take a little bit of time, you know, and so I would say assignments will probably take between 4 and 6 hours per week, you know, plus labs, plus classes, you know, so it is a fairly time-consuming class, but it's a cool class. So anyway, just to give you a heads up about this. By the way, do you have any questions so far, or no? Okay, cool. So this is going to be the schedule for the quarter. So the problem with winter quarter is that there are a lot of holidays, and we're pretty unlucky because they all more or less happen on a Monday, which means that we're going to have a lot of gaps in the schedule of the class. So on week 1, which is this week, today we're going to talk about the field of new interfaces of for musical expression in general. On Wednesday, we're going to talk about audio processing in Faust, and just to get you started with this. And our first lab this week will be about Faust basics and digital musical instruments in general. And there will be a very small assignment. That's why it's assignment 0. In fact, it's more like assignment -1, basically, you know, because there is no deliverable for this assignment. You know, it's just to sort of get you started with this. Anyway, so basically what's going to happen is that until week 6-ish, we're going to have proper sessions, proper classes. And after that, we're going to switch to final project mode. Once again, Music 258 is a class where students are expected to do a pretty big final project. And so so the last 4 weeks of the quarter are mostly going to be about critical feedback sessions on your final project and you working on your final project. We're going to have a bunch of guest lectures throughout the quarter. On week 9, Roger Lin will give a guest lecture. Roger Lin is the inventor of the drum machine, and he also has a company in the Bay Area where he makes musical instruments, such as the Linstrument. He's pretty famous in our field, so it's pretty cool that he can give us a guest lecture this quarter. We'll have a guest lecture by Ga Wang on week 7, who's going to talk about design and music technology in general. Mike will give a couple of lectures, and also throughout the quarter, Lloyd May will give us some small sessions on the accessibility of musical instruments in general. And in fact, Lloyd will speak at the end of the session today to give you some more information about this. I'm not sure if Lloyd is already connected, but I sort of told him to not connect until 10:30, so he's probably not there. Are you here, Lloyd, or? No. Okay.
I don't think so.
Okay, so Lloyd will probably join us later today. Okay. So before we get started with our first session, another thing that I want to say is that as part of Music 250A, you're going to get lab kits. And these kits include a lot of different things. I'm not going to detail everything you have in the kits, but basically you're going to have headphones, microcontrollers, sensors, and everything you need to do embedded audio processing and basic electronics. So you're all going to get your own kit that you get to keep at the end of the class. And also, I have some good news because there is something that was completely unexpected, but all students in Music 250A will get their own 3D printer, and Stanford will just pay for it. So thanks, Stanford. And this is as part of the P3D program that was started last year when the pandemic happened. And luckily, Stanford decided to continue this program this year, and they sort of just told us that Music 250A students will be able to benefit from that. So if you don't already have a 3D printer from the P3D program, because you can't really get another one, right? So those of you who didn't benefit from this program will get their own printer. We'll send you some additional information about this probably today or tomorrow, but basically what you have to do to get your printer is that you have to fill up a Google form on the Stanford website, and then they sort of give you a time where you can pick it up on campus, and I don't think they will be shipping them, right? Like so you're last year they shipped them to students, but this year since you're kind of expected to be back on campus even though teaching is happening remotely, you're gonna have to go pick up the printer just by yourself. Yes. Any questions about this, or still no questions? No? Okay, great. So we'll use Canvas for communication, right? So if we have things to tell you, we'll just reach out to you through Canvas. And if you have questions, you can also ask them through Canvas, right? Like, the drill. I mean, it's I think you're all pretty used to it at this point. So yeah. Very cool. Okay, so if you don't have any questions, then we can start with our first lecture, our first session, which is going to be about new interfaces for musical expression. And this is a lecture, so I'm mostly going to talk. It's probably not going to be like super interactive, but it's just to give you an overview of the field of new interfaces for musical expression, which is really at the heart of everything we're going to do this quarter. Cool. So by the way, you see here on the slide, so all the slides are available online. They are available on the course website. Okay, just before I actually do this, if you go back on the course website, if you go in lectures, and if you go in here, okay, there's something weird. Yeah, sometimes it happens when I share my screen. Okay, so here I'll post the videos, like the Zoom recordings of the class, okay? And you see that here we have resources. You can click on lecture slides, and so if you want to check the slides of this lecture later, you can do it. Okay, so new interfaces for musical expression. People also call that NIME, N-I-M-E, and it actually gave the name to a conference, which is the NIME conference, and you have a link to the website to this conference. And the reason why I'm talking about this is that potentially the different projects you're going to do this quarter are possible candidates for a paper for this conference. And so the last edition of NIME happened in 2021. The next edition is going to happen remotely in 2022 in June. So potentially, the different things you're going to do for Music 250A for your final projects could be things that potentially could lead to a paper and be submitted to this conference. So this is why I mentioned it here. Anyway, so So this is Jaron Lanier, and Jaron Lanier is sort of considered as the founder of the field of virtual reality. Maybe you never heard of him, but now he's, I think he's working at Facebook now, and so he's really like the person who sort of standardized the field of virtual reality. And beside doing that, he's also a classically trained musical instrument player. And so beside doing virtual reality, he actually talked a lot about musical instruments in general. And one of the things he said, which might seem very, very stupid here, is that musical instruments have the best interface. Okay, so if you think about musical instruments in terms of their interface and their sophistication, compared to most interfaces you're going to have in the world we live in, musical instruments are probably the devices made by humans that have the most advanced user interface. And that is also mastered by a lot of people, right? A computer keyboard is an interface, right? It's a fairly sophisticated interface, you know, like, but if you think about musical instruments, there are musical instruments that have an interface which is way more advanced than just a computer keyboard. And what's interesting about musical instruments is that not only do they have a very advanced interface, but they also are mastered by a lot of people. So it means that people are really willing to put time in actually learning that interface, you know. And you know, nowadays everyone is super lazy whenever it comes to actually learning how to use a tool or a computer or a device, right? But if you think about a violin, for example, it takes years before you can actually master the instrument, you know. And so musical instruments in the world of devices that are made by humans have a very special place in that regard, because people are really willing to spend time to actually learn how to use these interfaces. And so mostly in this class, we're really going to look at how musical interfaces are made, and also how they can potentially expand to other types of interfaces, because we'll see that there's really a very strong connection between the music technology industry and the rest of the industry. There were a lot of things that were made in music technology that were then exported to other industries, basically. And so I think this is something really interesting, and we're going to have a look at it a lot throughout the quarter. Okay. So I'm gonna talk about all this in a sort of a chronological way, you know, like just to sort of show you that what I just said here is true, and that I'm just not making it up. So what I just said has been mostly true for the entire history, known history of the humanity, and so I think a very good example of that is the hurdy-gurdy. So who never heard of the hurdy-gurdy? Say something. Okay, great, cool. So the hurdy-gurdy is a traditional European musical instrument that you mostly find in Central and Western Europe. And the hurdy-gurdy is a musical instrument that dates back from the 12th century. So it's a very old musical instrument. And even though it's sort of evolved through time between the 12th century, you know, like, and probably like the 18th century or something like that, you know, like where it's sort of stabilized, it actually didn't change much, you know, like, so the hurdy-gurdy that people are playing today are very similar to the one that people were playing at the 12th century. Okay, so just to sort of give you an idea what the hurdy-gurdy is, here's a video of someone playing the hurdy-gurdy with a funny t-shirts with too many assholes. Okay, and so here's the hurdy-gurdy playing. Can you hear it? Okay. Okay, so what do we have here? Sorry. So how does it work? You have a handle, okay? You turn the handle, and then the handle is connected to a wheel. And this wheel is bowing strings that are inside the instrument here. And so basically it's a bowed musical instrument, just like a violin or a cello, but instead of using an actual bow that you move with your hand, you actually activate the bow with the handle, okay? So that's the basis, but then it's way more complicated than this because there are many different sets of strings on the hurdy-gurdy. And so some strings are only connected to the bow when you press these keys. So these keys here, it's kind of this mechanism here, you know, like where basically when you press the key, you sort of cut the string in half, you know, just as you would do it when you play the guitar, for example. But except that here there is a keyboard that actually allows you to do this, okay? Then you have another set of strings, and these strings are basically just drones, and those are the strings that we heard at the beginning of the video. So those are the drones. So they're always playing, okay? And so no matter what you do, like when you turn the handle, the drones are playing, okay? And then you see that whenever you start turning the handle faster, other strings are being played. And these strings are called the dogs, actually. And see, he stopped. And so what these strings allow you to do is that they allow you to create some kind of rhythm, you know, like, so it's pretty hard to play the hurdy-gurdy because it's not just about like turning the handle, but like you need to give like these kind of impulses as you turn the handle to create the rhythm in the drone that you're creating by activating this very specific set of strings or not, okay, the dogs strings, okay. Anyway, so what I think is really interesting here is that this musical instrument that you see here, once again, is from the 12th century, you know, and as far as technology is concerned, this is a very, very, very advanced piece of technology for the 12th century, right? In fact, it's probably the most advanced piece of technology, or one of the most advanced piece of technology that humans made at the time, you know, and so there has always been a very strong connection between technology and music, and you know, nowadays we use our computers to make music, and so today we're really going to have a look at many different examples of that and see how technology sort of was used throughout time to make musical instruments. So once again, it's not something new. That's really something that dates back from the origins of music. You know, like people always use technology to make musical instruments. In fact, you know, if you think about this from an even earlier time, we're currently having a research project here at CCRMA about a cave in the south of France, which is called the Chauvet Cave, where there are paintings that dates back from 35,000 years ago, and people were actually playing music in this cave, and they found artifacts of that, musical instruments, you know, like that are made of bones, made of conch shells, you know, like, or things like this, you know, and so so even at the time, like just taking a bone, drilling holes in it, and turning that into a musical instrument 38,000 years ago, that was probably something extremely advanced from a technological standpoint to actually do, you know, like, you know. So anyway, this is really something that has always been there. Okay, so the next thing I want to say is that there is no universal interface for musical instruments. There are musical instruments that have interfaces that are optimized to do specific things and to be good at specific things, specific features, okay? And then there are others that are good at other kind of things and other kind of features. So if you think about a saxophone or a clarinet or pretty much any wind instrument. This instrument, in terms of interface, allows you to only play one note at a time. Okay, some of you are going to say, okay, if you're really good, you can play two, but it's not really designed for this, right? So a saxophone is designed to only play one note at a time. The thing, though, is that you can play only one note at a time, but you get a lot of control on the quality of the sound that you are producing. A saxophone is a very expressive musical instrument because it's not just about playing a note, but it's also about like playing the notes in a specific way. And to do this, you can interact with the mouthpiece of the musical instrument. You can interact not so much with the keys on a saxophone, but mostly with the mouthpiece. Like you can control like the breath pressure. You can control the opening of the mouthpiece. And you can change things using your throats as well, and so this type of interface here really allows you to get a very precise control on the sound that you are producing, but it only allows you to play one note at a time. On the other hand, if you think about a piano keyboard, it's kind of the opposite. With a piano keyboard, you can play multiple notes at a time. You can play super fast too. It's really designed for speed and for also playing a lot of notes at a time. But you have very, very, very little control on the sound that you are producing. And on a piano keyboard, mostly the only thing you can control is the velocity of the key, right? So loud, not too loud, and not loud at all, right? Okay, so some of you might say, and there has been studies about this, that if you are a very, very, very good piano player, you can sort of change the timbre of the keys if you sort of put your fingers in a specific orientation, or you give like a specific attack on the key or something like this, but this is extremely subtle, and in fact, it's not really completely proven. So basically, a piano keyboard allows you to play a lot of notes at a time, but with very little control on the quality of the sound that you are producing. So that's all. That is to say that basically you have different types of interfaces for different types of things you want to achieve with a specific musical instrument. Okay. So there's always been people making musical instruments that are not standards. Like this is what we're going to do as part of Music 250A. But 200 years ago, even before that, people have always been experimenting new musical instruments. And I think this is a pretty good example of that, because the instrument you're going to see here is basically a cello in which an accordion was integrated. So it's a mix between an accordion and a cello. It's from the 19th century. It's probably one of the only example of it. It was obviously not a very successful musical instrument. Okay, I'm gonna play the video. It's not played very well because this is Elliot Kermit. You guys probably don't know him, but Elliot used to be a PhD student at CCRMA until last year, and he doesn't know how to play the instrument right. He's just like playing it, but it sort of gives you an idea of the way this instrument actually works. Anyway, so this is weird, right? Like, I mean, it's like it's a cello, but you have an accordion keyboard, and you have this handle that activates the accordion, right? And so the reason why I'm showing you this, is that just to say that people have always been making musical instruments that are not so standards, and this is something we're gonna do in this class, and some of them, might actually become successful, and that's something that always happened in the history of musical instrument. Okay. So now we're moving in time, right? Like, as I said, I'm sort of taking a chronological approach to this class, so we started with a hurdy-gurdy. We saw this instrument, and the piano and the saxophone, okay. But a lot of things happened in the 20th century. right? As I'm sure you know. And the first big revolution that happened in the 20th century in terms of making musical instrument was the fact that musical instrument started using electronics and mostly electricity. So the first electrical musical instruments date back from the end of the 19th century, but they were really not standard. And probably the most famous example of in the first electronic musical instrument that, well, electric musical instrument that people actually knew was the theremin. So because you probably all know about the theremin, I thought I would show you another instrument which is very close to the theremin, but that is a little bit less known, and it's called the onde marteneau. It's a French musical instrument that was created by Maurice Marteneau in the 30s, and it really uses exactly the same technology as the theremin for sound synthesis, except that you can play it with a keyboard and more, as you'll see in the video. So what's interesting to see here is that as people started making musical instruments using electricity, they had to think about new interfaces to control these instruments. And the theremin is a pretty extreme example, you know, because you don't touch the instrument, you just control the instruments using your hands, right? The onde marteneau is a little bit closer to what people knew, right? There is a piano keyboard that the performer here is actually not using at all. There's a ribbon cable here with a little ring that you put on your finger, okay? And it basically allows you to control the pitch of the sound you are producing, but in a continuous way. So you can create vibrato, you can create glисsendos, slides, right? And a little bit like what the theremin was allowing you to do, except that here you get an absolute position of your finger on the keyboard, which is not the case with the theremin. You know, like, so the onde marteneau is way more playable than the theremin. And then you have this thing on the left here for the left hand, which is pretty cool. It's a controller that allows you to control the gain of the sound you are producing. So like the more you press it, the louder it's going to sound. And it's you can show. I tried to find a picture of this, but I couldn't find it. But the way this is designed is that there is sort of a rubber band that is suspending the key, and so it's kind of floating, right? And when you press it, you can move it in different directions. You know, like so. So this is kind of the ancestor of a joystick in a way, because you get X and Y control and Z actually on this little interface, which dates back from the 30s, right? So it's pretty old. So nowadays there are few people who know how to play the onde marteneau. It's the onde marteneau is kind of an interesting history, because it sort of became popular in the 30s and to some extent in the 40s in France, and actually all conservatories in France started having classes for onde marteneau, and you know, like I would say that in the 80s this sort of decayed, you know, and now there are very few places where you can still learn how to play this musical instrument, you know, but what's interesting to see, you know, is that at least in France, this musical instrument is probably the only musical instrument from the 20th century that was taught as an actual traditional musical instrument in music schools, and that's something that doesn't really exist anymore. Okay, so with acoustic instruments, form and function are deeply bounded. This is really something very important that we're seeing here. Systems used for sound production limits and influence the interface of the instrument. Okay, so what does that mean? It means that if you have a saxophone, as the one that we saw before, the place where the sound is being produced is more or less the same as the place where you control the instrument, right? It's the same for a guitar. Like if you take a guitar, you know, like the strings of the guitar are both the interface and the place where the sound is generated. Okay. The thing is, with modern musical instruments, this is something that is less true. And because there's the concept of interface and the concept of synthesizer, right? And as we'll see, this is potentially something that is problematic, and that makes our life really, really complicated as musical instrument designers. So there are examples of acoustical musical instruments where the interface and the place where the sound is generated are sort of decoupled, right? And I think a fairly extreme example of that is the carillon. So this is a video of Tiffany Ng playing the Charles Baird carillon at the University of Michigan. And Tiffany is, I think she's the only person who has a faculty position as a carillon player in a university in the world. There's really like a big carillon culture in the Midwest and also on the East Coast. Not so much on the West Coast of the United States. Like Stanford has a carillon, but I got this funny anecdote, you know, like where once I actually asked Tiffany if she played the Stanford carillon. She said, "Oh yeah, I played it, but you know, if you take all the bells of the Stanford carillon and you melt them into one belt, it's still going to be smaller than the largest bell of the Charles Baird carillon at the University of Michigan." So there's really something for carillon player, you know, about like having like big towers and big bells. That's what I learned from Tiffany. Anyway, so this is an instrument that takes a lot of effort to be performed, right? Like, because there is no electronic or electric assistance to play this instrument, right? It's really like your mechanical move on one of these keys that is triggering the clapper on the bell. And as I said, like the largest bell of the Charles Baird carillon, I think it's like 50 tons. So it's huge, right? And I think you activate it with the lowest key on the keyboard, right? And there is no electrical assistance for that. So like to actually play the bell, the 50 tons bell, you actually have to press super hard on the key. And so the point here, though, is that once again, you know, there is a decoupling between the interface of the instrument and the place where the sound is being produced. And another more extreme example of that is the church organ, right? So in the church organ, you have pipes which generate the sound of the musical instrument, and then you have the interface of the musical instrument, and the interface for the musical instrument is not necessarily close to the pipes. You know, there are even some churches where the pipes are spread everywhere in the church. You know, they're not necessarily all located in the same place. And then the organ player can select which set of pipe is going to be performed by pulling these little handles that are around the keyboard. Okay, so here with the church organ, there's a real decoupling between the interface and the sound production mechanism of the musical instrument, right? Because you can actually choose the timbre of the sound you're going to play by pulling one key or another, right? And so as far as traditional acoustical musical instruments are concerned, I think the carillon and the organ are really like the most extreme examples in terms of decoupling the interface and the sound production mechanism. Okay, Marc Battier is a French musicologist. You're going to say I'm only talking about French stuff, but it's not true. It's just that Marc Battier is he's actually like a very established and recognized musicologist. You know, like even in the United States. You know, like in fact, he taught at Harvard for many years. So I'm not saying I'm not talking about him because I'm French. Okay. Anyway, in his encyclopedia of musical instruments, this is what he says: from a human-computer interaction standpoint, DMIs, digital musical instruments, are instruments that include a separate gestural interface or gestural controller unit from a sound generation unit. So I think that's super interesting because in the eyes of Marc Battier, the defining component of a digital musical instrument is not necessarily the fact that it's digital or not, or based on a computer or whatever, but it's the fact that the interface is separated from the sound generation mechanism of the musical instrument. And I think that's super interesting, you know, because it means that in the eyes of some musicologists, you know, that is the main defining component of digital musical instruments. And as I said, as we'll see in this lecture and also like later in this quarter, this potentially can be a lot of problems for us. Anyway, so with electronic musical instruments, the concept of musical controller had to be created. And the keyboard you see here is just a controller, right? Like it's what we call a MIDI controller. I'm sure you know about MIDI controllers. But the point about a MIDI controller is that there is no sound in this keyboard, right? It's not a synthesizer. It's just something you plug to a computer or you plug to an external rack with a synthesizer. But it is just like it's just like a computer keyboard, right? But for music. So when did that sort of started? This all started when people started making analog synthesizers with voltage control. And here on the slide, you see a Moog synthesizer. It's a Moog System 35. And so basically, this is a completely electronic instrument. There is no computer in it. It's completely analog. And all the buttons and plugs and potentiometers you see here allow you to control the timbre of the sound, you know, and it's all electronic, right? So when people started making electronic musical instruments like this Moog synthesizer, they had to think about an interface to actually control them. And there were mostly two schools of doing this that sort of appeared. And so for those of you who are familiar with this history, you know, like basically they were the Moog synthesizers and the Buchla synthesizers, right? Buchla synthesizers didn't have a piano keyboard. Moog synthesizers had a piano keyboard. And so that's like the main difference between Moog and Buchla synthesizers, at least at the origin. You know, like, of course, there were different manufacturers with different circuits, etc. You know, like, but one of the main thing that sort of differentiated these two instruments was that basically. Okay. So you can see here on this instrument that the keyboard is separated from the interface of the synthesizer, but also the synthesizer itself, right? So that was the first example of an actual controller, you know, and the control was operated here using voltage control. And basically the sort of rule that was used for that is that 1 volt was equal to 1 octave, okay, for this type of keyboard. So basically when you press a key, you just create a DC voltage, and this DC voltage corresponds to a note or a frequency on the keyboard, okay? So that was their standard. Very basic standard, right? It's just DC voltage, and specific voltage corresponds to a note. So after that, they started making other types of controllers. So this is a not very well-known one, you know, but this is the Moog 1130, and it's basically a voltage control drum. So it's just a little drum, and you can plug it to your analog synthesizer. And you can play it with sticks and you can play it with hands, and it's the same story as for the keyboard on the synthesizer. You're generating a voltage, and this voltage is controlling something, right? So what I'm trying to convey here is that at that time, people started thinking of different interfaces to control different types of instruments. And what's interesting to see here is that this decoupling between the sound generation unit and the interface was sort of becoming greater at the time, right? Because it means that with one interface, you could control any sound synthesizer and vice versa, right? So later, digital technology came. And this is a picture of Max Matthews, who's playing the radio baton in his lab at CCRMA. And I mean, it's kind of funny. I didn't do it on purpose, but like you see this arch here, it's kind of the same as this one here. So this is well, actually, it's not really the truth. Like, because this was at CCRMA, and but this was in the basement. For those of you who've known the CCRMA building, or actually came to the CCRMA building, so the neuro lab of CCRMA, led by Takako Fujioka, used to be the Max lab, and that was at least 12 years ago, and or maybe like 10 years ago, and so that was basically Max's lab, you know. And the reason why the lab where I'm standing right now is called the Max lab is because it's named after Max Matthews. Okay. So who's Max Matthews? I don't want to talk too much about this, you know, like, but for those of you who've never heard of Max Matthews is the first person who synthesized the sound on a digital computer in 1958. He was working at Bell Labs on the East Coast. And when he retired from Bell Labs, he moved to the Bay Area, and he became a professor at CCRMA. And he founded the Max Lab, and throughout his retirement, he started making digital musical interfaces. And Max Matthews was one of the first person to do this, probably actually the first person to do this. So this guy had a crazy life. He invented sort of digital audio as we know it nowadays, and if he wasn't there, you know, like, you wouldn't have sound on your smartphone or computer or whatever. Everything that we're doing now would not be possible. And when he retired, just like if it wasn't enough, he actually started making the first digital musical instrument interfaces. And so the interface you see here is the radio baton. There is an example of one in the CCRMA lobby in the museum. And it's an instrument that works using capacitive sensing, and so you can basically detect the height of the sticks above the interface, and also you can detect the position of the impact on the interface, so X and Y, and yeah. So in 1958. The first sound was synthesized on a computer, and in 1962 was the first time a computer actually sung, and that's also the work of Max Matthews. I'm sure you've heard this before. If you haven't, because it's the first time you're taking a class at CCRMA, I just want to play this very shortly so that you at least hear that once in your life. So there we go.
For the love of you, this would be a Irish marriage. I had before the marriage, but you.
Yeah, so what do you hear here? Once again, is the first song that was sung by a computer. And they used the very basic physical model of a vocal track to do it. and it took days to synthesize it because they were doing it once again on a digital computer, which of course at the time could not synthesize sound in real time. So they had to pre-program the computer and wait for the sound to come out, you know. And since the entire songs last for about 2 minutes, it took weeks to actually get this recording here. Anyway, so 1958, 1962, and then a couple of years later, in 1975, Yamaha started a collaboration with, well, the collaboration started before 1975, but Yamaha had this collaboration going with CCRMA. CCRMA was the place where frequency modulation synthesis was invented. I'm sure you've heard about frequency modulation synthesis before, but what frequency modulation synthesis, sound synthesis, actually changed is that with very few elements, in fact, with just 2 oscillators, you could actually generate a very large spectrum of sounds, you know, like, you know, and in fact, with 5 or 6 oscillators, you can sort of mimic the sound of most musical instruments that are like traditional musical instruments. And so Yamaha and CCRMA collaborated, and then in 1975, Yamaha released its first digital synthesizer ever, which was the Yamaha GS1, and it was the first commercial digital synthesizer. There is one in the CCRMA lobby. It's a pretty unique thing. You should go check it out. Like, if you haven't seen it, you know, you know, there are so many cool stuff at CCRMA, you know, that people don't know about, you know, and if you see it like this, you're probably just like, yeah, whatever, you know, like, but there are only 3 in the world. One is at CCRMA, one is at Yamaha in Japan, and one is owned by Stevie Wonder. And I think the Yamaha one, sorry, the CCRMA one is the only one that still kind of works. And so go check it out. It's a pretty, there are people in other places in the world who would kill to see this, right? Like, and you guys like just have access to it, and it's in the lobby of CCRMA, you know, like, so just go check it out. So the thing with the GS1 was that it was insanely expensive, and so only like Stevie Wonder could buy it. So it was not really meant to be something that people were actually going to buy. You know, like it was more like a prototype to make something that would eventually become one of the largest commercial success of Yamaha, which is the DX7. And so basically the GS1 served as a prototyping platform for the DX7. And the DX7, which was released in 1983, is the first general public digital synthesizer that has been commercialized. And Yamaha made a lot of money with it. CCRMA made a lot of money with it. And this is one of the reasons why we have such a nice building now. And it's because of this keyboard. And the DX7 was really like the first digital synthesizer that people had access to. And people still use it, you know, like, I mean, the problem with the DX7 is that it was used so much in the 80s that every single song in the 80s sounds like the DX7, you know, and so basically, like, people don't really use it anymore because it sounds like it is an instrument from the 80s, basically, and it's a really cool instrument, though. So with the DX7, they were like, okay, now we have a digital synthesizer. It's going to be general public. So we need to have a standard to actually control these type of synthesizers, and a digital standard. And that's when MIDI actually came up, 1983, same year as the DX7. And what's really interesting about MIDI is that it's probably the only standard from sorry, there is the garbage truck outside, so it's probably Karma is not super well insulated, so if you hear weird sounds, it's a garbage truck. MIDI is the only standard from the 80s, not just in music, but in general, that is still used nowadays. Think about this, right? They created this standard 30, almost now, like 40 years ago, and people are still using it. It's only 8 bits, and it still works great, and we're going to use it as part of this class. So yeah. Anyway, so once they had a standard for controlling digital musical instruments, and they had digital musical instruments, then they could really do crazy things in terms of making interfaces to control these synthesizers. And this was a little bit more limited with analog technology, because you were kind of limited to this voltage control thing that we just talked about. But with digital technology, everything was possible, and that's when people started making interfaces for any kind of skills, of instrumental skills that people would have. So if you were a saxophone or a clarinet player, you would have your own interface, like the EWI here you see on the slide, which is an interface, a digital interface to control wind musical instruments. And you can use the EWI with saxophone and clarinet fingerings. It works, and this is a video of someone playing the EWI. And so once again, these stuff are from the 80s, right? So you saw a lot of those used in the 80s, and also in the 90s, maybe a little bit less nowadays, right? Because in a way they're a little bit funny, but there are a lot of people in the world who actually master these instruments, and maybe a bit less nowadays, but they do exist. So it was true for wind instruments. It was true for drum instruments. I'm sure you've seen electronic drum kits. So, same story. You have a skill, you have an existing instrumental skill. So you know how to play the drum, you know how to play the saxophone or the clarinet. Now you can play any musical instrument, or at least that's what they kind of thought. Anyway, so a little bit later, some companies started making more experimental things, and so what you see here is the Korg wave drum, and the Korg wave drum is a very unique instrument. It was the first of its kind, and probably the last that actually made a product. And very few people know about it because it was not a very I don't think it was a commercial failure, but it was definitely not a success. So basically, what's interesting about this instrument is that it's combining acoustical and digital elements to create one musical instrument. So you have a real drum membrane, and this drum membrane is connected to contact microphones, to piezos, right? And so when you create sounds on the membrane, these sounds are picked up by the contact microphone, and then they are sent to digital resonators. So digital resonators are basically just like filters that are resonating and that are implementing modes of resonance of a musical instrument. So what's really cool about this instrument is that you get acoustical excitations. So what actually makes the sound comes from the real world, and then it drives things that are completely digital. So you sort of get the best from both worlds, basically, and so here is a video, someone playing the wave drum. So depending on where you tap on the membrane, you get a different sound. And you can, of course, change the sound of the instrument, which is pretty cool, depending on if you use sticks.
Michael Jones here with Craft Music. Today we're going to... The global edition is Korg's third. Let's get started by listening.
Okay, sorry. So you can change the timbre, the sound of the instrument. You can use any kind of elements you want to play the instrument. You can use sticks. You can use your car keys. You can use your fingers. You know, like anything. You know, it's gonna sound different, just like on a real musical instrument. So we're gonna have a lab as part of Music 250A where we're gonna try to make hybrid instruments like this one. So basically where we use contact microphones, piezos, to pick up sound from different types of surfaces, and then implement our own synthesizer controlled by these sound excitations that you're getting from the instrument. I think this is gonna be lab 3. Anyway, so now we're getting closer to nowadays, right? So in the 80s, people were making all sorts of interfaces to control their digital musical instrument. But then more recently, people were like, okay, we're going to try to make universal interfaces. And that's kind of the idea of the C-board. The C-board is kind of I don't think it's the first of its kind, because I think the Continuum keyboard is older than the C-board, and they're kind of similar in many respects. But the C-board is probably the most famous of all of them. So the C-board is this. Okay, I'm gonna play the video just so that you sort of get an idea. Anyway, so basically what the C-board does is that it's a keyboard, just like a piano keyboard, right? But it also has continuous control. So it means that it knows where your finger is or your fingers, because it's polyphonic, you can use multiple fingers. It knows where your fingers are on the interface, X, Y. And then this interface is kind of this rubbery thing. So like as you press more on it, you know, like you get more sound basically, right? And it is kind of a weird instrument. In the video, the person you see playing the instrument here is Jordan Rudess, who's the keyboardist of Dream Theater. It's a pretty famous rock band for those of you who know about it. And Jordan Rudess is kind of the official demonstrator of all these sort of exotic digital musical instruments. And some years Jordan does a guest lecture in 250A, but I think he was a bit tired of doing remote stuff. So this year he was like, no, I don't want to do remote stuff. So I'm not going to do it. But anyway, last year he did, if you want to watch the class from last year, it's still on last year's website by Jordan Rudess. And he says all the good things he thinks about this keyboard, and they're not so good. So it's kind of interesting to get that kind of insights from the people who actually demonstrate them. Anyway, the reason why it's weird is because first you don't, well, at least that's my take, right? Like I'm a piano player, so I think I know what I'm talking about for this. You know, like the first thing is that you don't really see the keys, so it's kind of a problem. You know, like on the keyboard, it's pretty clear where the keys are. You know, like here, you don't really like feel them properly, and then it's kind of soft. You don't really have haptic feedback. You know, like and so it is a weird instrument in many respects. You know, but many people bought it, but eventually I think Raleigh went bankrupt because they didn't really sell enough. Right. So it's an interesting story. Okay, this is the Lynn instrument, and Roger Lynn once again is giving a guest lecture in Music 250A later this quarter. And the Lynn instrument is also a continuous X, Y, Z musical controller, but it takes a completely different approach than the C board. And like personally, I think it's much better. And it's based on an isomorphic keyboard. So it's like a matrix of keys, and you can kind of reconfigure it the way you want in function of what you want to do. You get pressure, but it feels better than the keyboard because it's not as soft as the keyboard. And so here's what it does. Okay. I'm just gonna, yeah. So if you hook it up to a good sound synthesizer, then it's it's doing pretty cool. It's doing pretty cool stuff. And in his guest lecture, usually Roger sort of describes how this instrument is built, like from a purely engineering standpoint. So he's going to bring the instrument, and he's basically going to open it and show you what's in there, And so this is super, super interesting. Usually students really like this lecture. Okay. Here's another one. So this one is also interesting. It's called Touche. It's by a company called Expressivy, and basically what Touche is that it's this thing that you put aside of an actual MIDI keyboard. And okay, I'll play the video so that you know what I'm talking about. So it's kind of a very simple idea made by French hipsters, as you probably just saw, and so basically it's based on the same technology as the technology used in the Onde Martenot that I talked about earlier, and it's basically just a key suspended with rubber bands, and you get like X, Y, right? And also you get Z if you press on it. And because it's very finely tuned, you really get a lot of precision, and it basically allows you to get velocity control and stuff like this on a piano keyboard that you would not necessarily have, and so that's kind of interesting. So the same company released a year ago this keyboard, which I think is pretty cool. It's called the Osmose keyboard. It's very expensive, as all these things usually are. And so basically what the Osmose is that they basically took the technology they had for the Touche, and then they made a keyboard with it. So every single key of the keyboard uses the same technology as the Touche. So it means that it's a keyboard with floating keys. So if you take a key, you put your finger on it, you can sort of bend the key if you want to create vibrato. And you also get like pressure sensitivity on all the keys. So essentially what they tried to do with the Osmose is that they tried to fix the problems of the keyboard, right? Because on the keyboard, you had no proper mechanical haptic feedback. And it really feels weird for a piano player to play the keyboard. The Osmose sort of addresses this problem by still having like mechanical keys, but that you can bend in multiple directions. And so yeah, I think that's an interesting approach for sure. And, I don't know, that's like the best example. Okay, here's Jordan over this again. See the vibrato?
This is a whole new world.
Anyway, so that's kind of the idea. I think that's interesting, you know, like, but basically what all these people are trying to do is to create a universal instrument that can control them all, basically, right? And because you know, if you try to control a saxophone sound with a basic piano keyboard, it's just not going to work, because you miss all the expressivity that you have in the saxophone mouthpiece, right? And so this is really a problem that people sort of slowly figured out in the 90s and in the 80s as they were making digital musical instruments. You know, at first they were like, okay, cool, I'm going to be able to make a synthesizer that can play any musical instrument, right? And I don't know if you had that when you were a kid, you know, like, but like when I bought my first digital keyboard, that's what I thought. You know, I was like, cool, I'm going to buy this Yamaha keyboard and then I can play an entire orchestra with just a single keyboard. And then you play the instrument and you're like, yeah, it sounds like shit. I don't really know why, but the sounds are not so good, you know, and the sounds are not so good because you're trying to play a saxophone or a clarinet using a piano keyboard. It just doesn't work, you know? And so so that's kind of what they try to solve with these type of interfaces. Okay. So here are other examples, you know, like, you know, now we're sort of slowly going towards things that are a little bit more, I would say, exotic and a little bit more experimental before we move on towards what people actually do in academia, because so far we have only been talking about what has been done in the industry. So this is another startup called Mojis, and I think it doesn't exist anymore. So you'll see there is a really sad truth about our field. And it's that if you make a startup to make music technology, your chances of failure are pretty high. And so like all the startups that I'm talking about, like most of them actually stopped, which is kind of sad. But anyway, so the idea of Mojis is that you have this contact microphone, you can put it on any surface, and it's going to turn it into a musical instrument. So these are again more hipsters playing music on a tree, just as before, and so enjoy. Hipster walking in a forest, and then he finds a fence. Okay, it's better than a tree. Anyway, well, you get the idea. So that's Mojis, and so this thing does two things basically. Pick up the sound that you create on a surface. Then it feeds it into a resonator, just like the wave drum we talked about already before. But in addition to that, it does machine learning to actually sort of detect where you are tapping on the surface, right? So if you put this contact microphone on a tree, depending on what branch you're tapping or like what part of the body of the tree you're tapping, the sound is not going to be exactly the same, right? And so they use machine learning to sort of figure out where you are tapping on the tree. And so then you can sort of create zones, you know, and you're like, okay, this branch is going to be mapped to this sound, and this branch is going to be mapped to this sound. So it's pretty cool, you know. It's kind of a cool idea, and but it didn't work. And I think they recycled this into another startup for domotics. So basically you have a kitchen counter, and depending on where you tap on the kitchen counter, you sort of activate your oven or stove, or I don't know. Anyway, so at least it was used for something in the end. Anyway, so that's what happens in the field, well, for the industry. And now I want to talk about academia. But before I do this, is Lloyd here? Lloyd?
Hello.
Hi, Lloyd. Welcome.
Howdy.
So yeah, I already told everyone you were going to say something. So please take as much time as you want. So
Awesome. Thanks so much for having me. Would it be cool if I shared screen?
of course, I'm going to stop sharing my screen, and now you can share yours. Yeah.
Awesome. Let me just quickly get that set up. Cool. There we go. Alrighty. Howdy, everyone. I'm Lloyd. I will be chatting to you guys very briefly on a bit of the why of making some new instruments. So Roman's been giving this really great overview of industry and some new instruments that have cropped up, hopefully getting everyone excited. And so I'm going to start the conversation of why we might make these new instruments, and specifically why we might think about cognitive and physical accessibility when making instruments. So sorry, let me just grab the other window. There we go. Sorry about that. Alrighty, so I'm Lloyd May. I'm a PhD candidate at CCRMA in my second year, and my research focuses mainly on accessibility, disability, and interactivity. So if you dig any of those things, feel free to come chat to me. And I'm also from Carletonville, South Africa. It's a small mining town, and that's where I currently am. So hello from Carletonville. So to kick this mini lecture off, I'd like everyone to write in chat if possible. So you can just write it up and don't press send yet. And just answer the question, why make new instruments? And so you can interpret this as, why do you want to make a new instrument in this class? Or why do we, as humans, as people, weird people in universities, make new instruments? So I'll give that about 30 seconds. Feel free to queue up your response. And then when I say send, you're going to flood the chat. We're going to have a quick look over some of the answers. Alrighty, so we'll give it another 15 seconds on my watch. Oh, and it looks like Ramon is in the Max Lab. That is super cool. I'm very jealous. Alrighty, so start wrapping up those last couple words, and then we're gonna bomb the chat in 5, 4, 3, 2, 1. Send it away. Oh, beautiful. Okay. Oh man, I just saw Nima's one first that said fun. Oh, that's fantastic. Sweet. So we've got some awesome replies if folks want to thumb through the chat to make cool sounds, to make new or creative sounds, keep evolving with communication and expression, self-expression, different avenues to make music. It's all really great stuff. Express individuality. That's a really interesting one. Human expression, new methods of expression. Awesome. So we've got quite a swath ranging from, sort of broad cultural new ways to express yourself right down to individual and I just want to have fun. And so those are all really epic reasons to want to make new instruments. And the one I'll briefly be talking about today is because we don't currently have the instrument that we want or need. And I know this kind of seems like a cheap answer. Why are we making the new instrument? Because it doesn't exist. And so I'm going to, instead of asking you to bomb the chat again, thank you very much for doing that with me. I was going to go over some common reasons as to why we don't currently have the instrument, that you might be thinking of in your head. The first one, like I think Roman explained very nicely, is often too niche. There's not much of a market for maybe these very specific instruments, or they're super expensive. Maybe no one has thought about it yet. We're just a group of cool new designers. The making of it is the real instrument. This is a great answer I got in a workshop I previously taught, and it's very meta, and I appreciate that. And then the last one, and again, sorry, a bit of a canned answer, is that if your mind and or body doesn't behave in the way designers expect, instruments might be more or less challenging for a person to access or play. And so I'll go over 2 super quick examples of some pretty famous accessible instruments, and then just give you my contact info. I'll be popping out throughout the quarter to talk about physical and cognitive accessibility. And if you have any questions around any of that, please feel free to reach out to me. But the first instrument is from Drake Music. They're a NGO based in the UK, closely affiliated with Queen Mary University. And here we see John Kelly on the left and Gavin Hewitt on the right. And that is the Kellycaster. I'll pop up in, I think, week 6 to tell you a bit more about this instrument. But it's great in that it looks and sounds like a guitar, and it's one that John can play, and he plays a bunch of, really awesome pub gigs, and it's just like a classic Bruce Springsteen kind of person, but now has a guitar that works for his body. And the last one I'll quickly mention is more of like a collection of accessible instruments, and one that Patricia Alessandrini, who's a professor at Stanford and CCRMA, did in collaboration with Share Music. And so this is a whole suite of sensors, much like we saw with that machine learning one that you could use to play the tree. These are all different types of byte and piezo sensors that a mixed ability ensemble used to realize a really beautiful, intricate piece. So hopefully that's like a quick lightning overview of the field, and just get people thinking about why we might want to make these instruments, and one of those reasons being accessibility. And yeah, if you're excited about accessibility or want to know more about disability more broadly, or even on campus, please feel free to reach out to me at lloydmay@stanford.edu. And thank you very much for having me. I will stop sharing.
Cool, thank you, Lloyd. So, so one thing that I want to say is that Lloyd is gonna pop up in multiple classes we're gonna have throughout the quarter, and because we think it's an important topic. So, so basically, yeah, Lloyd will be back, and I also kind of want to encourage you to maybe for final projects, like to take that kind of things into consideration, right? Like, it's totally fine for a final project, like to be doing a final project centered around accessibility of musical instruments, right? Like, so in fact, I would kind of encourage you doing that, and I'm sure Lloyd can help in that, in doing that. So yeah, cool. Well, thank you, Lloyd. Very cool.
Thank you.
So I'm going to share my screen again, and I'm going to try to wrap up the lecture with the last part of it, which is about what we do in academia and the field of new interfaces for musical expression. So unlike in the industry, there's an infinite number of possibilities. We are not limited by the market. Means that we just do what we want. If we want to make an instrument that no one is ever going to play, it's okay, we can do it. The main drawback, as you can imagine, is that it's very easy to miss the point. And I think this is something that is true for this field of musical instrument design, but it's also true with digital technology in general, because you can do so much. It's very easy to make something that kind of misses the point, right? Or that is useless or whatever, So as you make musical instrument this quarter, I would really strongly encourage you to think about that. Like if you're like, okay, I'm going down the rabbit hole, I should just rethink what I'm doing, because it's never really going to work, or it's never going to be really like successful, and so that I think that's something that is really important to keep in mind. Another thing is that technical complexity doesn't mean quality, right? Very often something extremely simple is better than something that is going to be extremely complicated. The problem with this class and our field in general is that, as you'll see, you're gonna get pretty excited about what you do. At least I do. You know, and so it's very easy to start making an instrument for yourself, just like to please your personal need for making pieces of engineering, because it's just cool to do it because we're all nerds, right? But then on the other hand, it's not necessarily a good idea to do this, right? Like, because maybe once again you're gonna miss the point. So never forget that it's up to the performer to make an instrument sound good. Musical instruments are just a mean, it's not an end, right? So basically, if you're a good performer, you can take a plate, a fork, and it's probably going to sound better than any of the instruments you're going to make in this class, right? So I think that's something that is really, really, really important to keep in mind. You know, like, we're only here to make tools for musicians. That can be yourself if you're a musician, but like, keep that in mind, because I think that's really, really important. Anyway, so I think the first example of digital musical instrument in academia is the radio baton that we already talked about before. So I would say that there are two main approaches that we're going to use this quarter to actually make these musical instruments. And the first approach is the junkyard / recycling approach, which is a form of top to bottom approach. Okay, so what does that mean? By the way, this is a picture of the CCRMA garage. The CCRMA garage host a lot of heavier tools that potentially you could use for your final projects. We have a CNC machine, we have a bend saw, we have a table saw, we have a welding station, you know, that kind of stuff, you know. And so if your project potentially requires this kind of elements, I think I'll be very happy to show you how it works, you know, and to sort of give you a quick training on how to use some of these tools. Anyway, so the junkyard approach is basically, you have an idea, you know, like, you start from an idea, and you don't really think about what you need to actually reach that goal, right? So it's a top to bottom approach, right? You start from the top, you're like, okay, I want to do this. I don't really know how I'm going to do it, but that's what I want to do. And then you start looking for things that will allow you to implement your idea. And this is Perry Cook's coffee mug. And it's this picture is taken straight out from Ga Wang's book, which is the textbook for this class. And basically what Perry did here is that he was like, okay, I need an instrument, an interface, which has a cylinder shape. It has a bunch of sensors on it. And so I'm just going to take a coffee mug, because that's the best thing that I found to do this. You know, like, it has a handle, it's circular, it has the cylinder shape, and then I'm just going to put a microcontroller in it with a bunch of sensors and FSRs and etc. And then I just put duct tape everywhere so that it holds in place together, and that's your instrument. So that's the junkyard approach, you know, because it's like, okay, start from the top, have my idea, and then I'm just going to use existing elements to actually implement my idea. And in the Max Lab, there are a lot of things that you can potentially reuse to make your musical instrument. Okay. So this is, I think, a pretty good example of that. And I think it was a very meaningful example, and also just experience in general for me. So this is Ken Butler, and he's performing, well, it's a picture here of him performing a golf club. And basically it's a golf club with a string mounted on the golf club. There is a piezo, so a contact microphone placed at the bottom of the golf club. And then you can, you know, you can bow it, you can play the string, you know, and that's the instrument. So the reason why I said this is kind of a very meaningful example to me is because in 2016, I went to the Goffman Musical Instrument Competition, which happens every year at Georgia Tech in Atlanta. And so, well, for the past 2 years, I think it's gonna, yeah, it was happening remotely, you know, like, but like other years, it's kind of this big show. It goes on TV, you know, and they bring like famous people to be part of the jury. There are a lot of people participating. It's a really, really cool thing to see. So if you're interested in this field, you know, like I really strongly recommend you to if you have something to show, to actually apply to this musical instrument competition. So what happened that year in 2016 is that you know, as usual, people showed up with a lot of gears and very complicated musical instruments. I remember these Australian guys coming, you know, like from the other side of the world with like 5 cases of gears to actually make their musical instrument work. And then there is this guy, Ken Butler, who's a New York-based musical instrument designer, who just shows up with his golf club and a looper and a guitar amplifier. Okay. And then he did a hell of a performance. He was so good. Like he really, like that golf club sounded so good. And unfortunately, I tried to look for a video of it, but I couldn't find it. So I'm really sorry about this, but like it was mind blowing. You know, like it sounded like so many different things. Sounded like an Indian tabla, and then he played rock with it. You know, it was really, really brilliant. So of course he won the competition, you know, and so basically all these guys who came with these super advanced pieces of technology were kind of mad, you know, because this guy showed up with his golf club and, you know, string that he probably just made in one day in his garage, you know, and he won the competition. And he won the competition not so much because his instrument was good, but mostly because he was a good performer, and that because also because his instrument was giving him enough affordances to do what he wanted to do, you know. And so once again, you know, like I think the lesson to take from this is that it's not because an instrument is technologically advanced that it's going to be a good instrument, right? So another example of junk art approach is the work of John Granzo. So John Granzo used to be a PhD student at CCRMA a while ago, and now he's a professor at University of Michigan. And so John worked a lot on sort of recycling day life objects, you know, into musical instruments. So this is a coffee percolator from an espresso machine turned into a Java lily, and he used 3D printing to sort of add elements to the percolator to turn it into this little banjo. And inside of the banjo, you have a small sound processor that implements like distortion and audio effects. And funnily enough, the hole for the coffee to get out was just big enough to press fit a jack cable, so you can just like plug it to your amp, you know, and you know, just food for thoughts. So that was the junkyard approach. Then there is the technological engineering and research approach. Okay, so that's kind of the other way around. You know, like it's like we try to have a more pragmatic approach to making these musical instruments, and we start from the bottom basically. I think sorry, it's not Davide, it's David Wessel and his slabs. So David Wessel used to be a professor and also the director of CMAT, which is the brother of CCRMA, but at Berkeley on the other side of the bay. And David Wessel worked a lot on making custom musical interfaces using advanced technology. And the slabs is a good example of that. And so it's a little bit like the Seaboard. It's like a pressure sensitive instrument. And so what David wanted to do with this instrument is that he wanted to make an instrument, that would be like as fast and as precise as possible, so that if you wanted to do like a drum roll on it, you could do it, like for example. And so it was not using MIDI, it was actually using audio to convey the different signals that you were getting from the instrument, because MIDI didn't have sampling rates high enough to actually do what you had to do with this instrument. So there is a paper about the instrument that you can find on the web easily. If you're interested in that kind of approach, I recommend you to have a look at it. Okay, this is Dan Truman's bossa, and so the bossa is basically a sort of cello type of instrument. So it's not really designed to be necessarily beautiful from a purely design standpoint, but it is a beautiful piece of engineering, because you know that a speaker produces a signal that is completely directed. It only goes in one direction. But if you take a cello, the sound that is produced by the body of the cello sort of radiates in all directions, right? And so the main idea, or one of the ideas behind the bossa, was to create a cello type of interface that radiates sounds the same way as a cello, basically. And so I don't know if some of you know about Slork, but you probably sort of recognize the shape of the speakers because they are close to the speakers that Slork is using. Because Dan Truman was at Princeton University, like where the first laptop orchestra was created, and the speakers from the laptop orchestra came from this design here, and so I think this is this is kind of interesting. Okay, this is Charles Nichols' Vibo. So it's Charles Nichols is now a professor. I forgot where he is, but like he's a professor somewhere. He was a PhD student. He was a PhD student at CCRMA as well, and he made an interface to control physical models of a violin with haptic feedback. And there is a paper about this instrument as well, and sorry, the picture is pretty bad, but that's the only one I could find. And I think it actually originated, it started from a 258 project, and then it eventually became his PhD project. So there is a paper about it. If you want to know more about it, I recommend you to have a look at it. Okay. So this is another example of a startup that died, but that started from an academic project at IRCAM in Paris, where basically they try to do active control on the body of a guitar so that an acoustic guitar could sound just like any guitar, basically. So if you wanted your acoustic guitar to sound like a jazz guitar, or sound like a nylon string guitar or a steel string guitar, you could do it by doing active control on the body of the guitar. And you can also add audio effects to the acoustic guitar itself. So like the whole idea, again, is that potentially you can also have like a flanger or a distortion or something like this directly coming out of the body of the guitar. So I think that's a interesting example. Okay, I'm gonna skip that example because I'll talk more about it later. I'm just like spinning it up because we're running a bit out of time, and I'd sort of like to finish this in time. Okay, this is Rebecca Fiebrink, and Rebecca Fiebrink has been working a lot on the use of machine learning for musical interfaces. And there is a whole field behind this now, part of the NIME community. So if you're interested in that, like just look up for her name on like Google Scholar, and there are a lot of papers, that will sort of give you an overview of what people are doing in this field. Just so you know, in 258, we're not going to do too much of that. So because we don't have time to do everything, if we wanted to do everything, we need like 3 different classes for it. We need a 250A, B, and C, basically. I think that's what we need. Okay, so new musical instruments are not just musical instruments; they can also be art installations. And I'm sure you've all seen this example before. Kind of went viral at some point on social media. Anyway, I think that's pretty cool, right? Like you've seen, I'm sure you've seen it. This guy probably spent so much time designing this thing, right? And it's kind of crazy that it actually works, and probably requires a lot of tuning pretty often. So anyway, this is another example of what people would do in academia. You know, like it's like people would also make instruments which are sort of halfway between an instrument and an actual installation. This is Coca Nicoladz's beat machine. Coca Nicoladze made a lot of musical instruments of this kind. If you Google his name, you're going to be able to find more. This one is a bit old now. I think he made it like 4 or 5 years ago. So that could totally be a 258 project. Anyway, okay, this is something a bit more ambitious. This is a fire organ and Maker Faire, and it's controlled by a wireless guitar. It doesn't necessarily sound very good. But it was very successful. People liked it. So we tried to have this person come to CCRMA, I remember a couple of years ago, but the fire marshal at Stanford never allowed us to do it for some reasons. Anyway, so what do we do from here? We're going to learn how to synthesize sound on a computer, and we'll use the Faust programming language to do that. We will create standalone and embedded sound synthesis and processing systems. We will control sound synthesis in Faust using sensors, learn basic electronics, and work with microcontrollers. And in our case, we're going to be using the TNZ. We're going to prototype instruments and interfaces. We're going to learn CAD modeling in OpenSCAD to prototype more advanced instruments and use digital fabrication to make the final product. And finally, we will design our own instrument interfaces, installation, and finally showcase them at the end of the quarter. Anyway, I think that's pretty much it for today, guys. I'm sorry, maybe this was a bit boring, because I've been talking a lot, and it's probably going to be the only class that's going to be like this. Like the next sessions we're going to have are going to be more hands-on. And in fact, on Wednesday, we're going to start writing code in Faust together. So this is going to be a little bit more interactive. Do you have any questions?
Sorry, I had a question. Hi.
Yes.
Do we know the dates for the showcase at the end of the quarter?
I think we know them. They are already on the website in the schedule. And let me check. Final presentations, March 7th.
Okay, sorry, my bad. I should have.
It's the week before finals week. So
okay.
Yeah, we always do that because it's kind of hard to schedule like a big showcase during finals week because people are super busy. So it means that basically this ends on week 10. Basically, like there is no like finals week for it, and there is no like proper final for this class. So yeah.
Thank you.
Sure.
I had another question. So one of the points you mentioned is like to design an instrument that, you know, will sound good. Are we designing like the synthesizing part, or are we are we like designing just like a MIDI interface? Because it seems like those are kind of different things.
You're going to design everything.
Okay.
So you're going to design everything. So like the goals for Music 250 are pretty open-ended. So so if you want to focus more on the interface side of things, you can. And if you want to reuse like an existing synthesizer or something like this, that's totally something you can do. But if you want to like make like a comprehensive musical instrument like from scratch, which is not necessarily an interface, but like an actual instrument, you can also completely do it. So with the stuff we're providing in the kits, you can make MIDI controllers, you can make embedded sound synthesis processing directly on the microcontroller itself. So so we're going to do both in the class, but for your final project, it's completely open-ended. So so yeah.
Thanks.
Sure.
Hey, I've got one more question. I was just wondering this is just a logistical question, considering the 2-week period of online teaching, at least that's what we know so far. Who knows what will happen. But for those of us who do have building access during the first 2 weeks, would it be possible for us to go into the Max Lab, or like, I actually don't remember if CCRMA has made an announcement or something like that, but whether or not we can go in?
I think that's possible, but I need to ask. So I'll ask the building manager this morning, and I can yeah, I'll send you I'll send everyone a message like this afternoon about this. Yeah, good. That's a very good question. In any case, you're not gonna. So we're gonna give you the kits on week 3. So we're not going to do any hardware until week 3, basically. So like in theory, you don't really need the Max Lab for the first 2 weeks, but if you want to come in the Max Lab and work, you know, and start exploring what's there, you know, like that's totally okay. So so I need to ask if it's possible to give people access to the building in case you need it. Good question.
Thank you.
Dirk, I see you. I see your lips moving, but I cannot hear you. I think you should restart Jack, Dirk. No, don't restart Jack. We don't know. Yeah, we still don't hear you. Okay. Well, never mind. Any other questions? Okay, well, thank you guys. If you have other questions, you can send me an email. You can send an email to Mike too. And I'll see you on Wednesday then. And yeah, thank you.